All right, there you go. Thank you for inviting me to give this talk. I was asked to specifically address ultra-fast switching of antiferromagnets, which I will not do. Sorry for that, but I will give an introduction on how we can use optically induced spin currents to maybe address ultra-fast switching in the future. So the talk is ultra-fast spin current generation for antiferromagnetic switching, and in my abstract in rare earth ferromagnets, which I will address a little bit, but I took it out mostly. So this talk, 25 years of ferromagnetism, femtomagnetism, let's put it that way. The next 3 days, there will also be a symposium in Nijmegen of Theo Razing, 50 plus 2 years. Well, it all started also on that part. So what do? We excite something at a certain temperature, magnetization, we excite it, delta T, M decreases, and you have something that, where is this angular momentum going? Right? This question has been asked for quite a while. And yeah, timescales, processes, and I think we heard quite a bit of it on this talk today, but also in the future, what will happen there and how we can use it in the future. Right? So the basic part is conservation and transfer of angular momentum. So you hit the stuff with a probe laser, you get all kinds of effects that are combined, X-rays, etc., to probe what is really happening in the system. And then a long time ago, spin polarized photoelectrons were studied. And I also want to claim today that we can use the ultra-fast spin currents that are generated by these ultra-fast currents to maybe address ultra-fast switching in antiferromagnets. Some acknowledgements here. So this is our group, Physics of Nanostructures. Our group chair is Bert Koopmans. Colleagues, Diana Leitao, Henk Zwachte, Rembert Duijnen, and Jos van der Tol. These are all the people who are doing all the real hard work in the lab. So everything that I show is due to these students. We are just there to guide them. So this is the acknowledgement of everything. Of course, our collaborators in Nancy, Beijing, but also in all the networks in which we are included. I always forget acknowledgement, so I put it up first now. All right, so let me start with the dream device that we have in Eindhoven. Now, let me just check out this part. Yeah. I'm an applied physicist. I like to work on device physics. So at the moment, all the information over the world is mostly transported in photonics, right? Glass fibers going through your home, your internet is coming in. It's transferred to your computer, a lot of electrical translations between all the phases that you have, so we lose a lot of information. So what we're trying to do in Eindhoven, also included in the Institute of Photonic Integration, is actually to go directly from the photonic domain to the magnetic domain, right? Now you can think of this as a kind of shift register where you have a pulse of light going through a light guide. On top of it, you will have a kind of racetrack memory, and you directly write the information in the optical domain to the magnetic domain. The only problem is that this photonics is already at the 100 gigabits per second rates. And this is something with ferromagnetism that is very difficult to do. So we might need antiferromagnetism in the future to really address this. Yeah? So I like to think about this direction. So we need a right materials platform. At the moment, we are still working on ferromagnets, to be honest, on synthetic ferrimagnets, because those show nice switching, and you can get very high domain wall velocities going through. But of course, the combination using antiferromagnets might be a very nice marriage of the two fields. So what is the current state of the art? If you think about the materials here, the photonics is all well defined. So integrated photonics already works at these high rates. The stuff on top, the magnetics, so if you look at synthetic ferrimagnets, so for instance, the materials that Stuart Parkin has introduced, etc., domain walls flying through at 2.5 kilometers up to 5 kilometers per second is proven. That's state of the art at the moment, right? But this is still not enough to go to the very high gigabit rates, because the domain wall width, etc., you have to play with. Antiferromagnetic are nice. It has a low threshold fluence, but it needs to be lower even further. Yeah, so these synthetic ferrimagnets, to switch them, you need very little energy nowadays to actually really write the magnetism, but we still need another few orders of magnitude. Recently, by the group from Eisenbit and also ourselves, has shown that we can rewrite the magnetization 2 pulses after each other within 10 picoseconds. This is all still based on heating, so not very energy efficient yet, but we still have to work on this part. But we show that you can do it within 10 picoseconds. Still not enough to go really to these gigabits per second. We're getting there, but preferably we would like to do it with 1 picosecond. Moreover, you have to play around a lot with the engineering of the heat sinks. to get rid of the heat fast enough before your second pulse arrives. Right? So we need the right materials platforms, and I think in the future we might want to use everything that we have seen in this workshop for these kind of devices. Sorry to be a bit blunt there, but it would be a nice concept. All right, so a little bit of the outline. I'll give a little bit of a tutorial introduction on how these materials are based, and then I'll show some 4 new results that we have based in our group, mostly based on the work from Bert Koolmans. All right, so a little bit on the background. It started 96. We've seen this one quite a bit before, where you look at nickel, the demagnetization, ultra-fast demagnetization within 0.2 picoseconds, and then a remagnetization. And this can be very well understood by the 3-temperature model. Now, you can also look at how this works, right? So if you have all the angular momentums in this system and how they play with each other, you can really model it in a very intuitive way, I would say, how this angular momentum is transferred. If you look at gadolinium, for instance, the other material that is ferromagnet at room temperature, or more or less, you see the same thing, a first drop, very fast, and then a very slow remagnetization or demagnetization afterwards, because the electrons work in a very different way. That thing you can model also with a kind of 3-temperature model, only you have to now take into account through 2 spin baths of the different spin species, and thereby we can understand these different time scales in these materials. So this is a bit the playground that I will show you. Play around with the fast nickel, iron, cobalt, and the slow gadolinium in this case, but it's a general feature of the rare earths. Okay, now, this is all about local transfer of angular momentum. What about non-local transfer of angular momentum? So back in 2008, Malinowski et al. Showed that if you demagnetize a system, for instance, 2 platinum cobalt repeats, either spaced by nickel oxide, an insulator, or by a metallic system, you can manipulate the demagnetization times. Right? This is an insulator spacer, so the spins will not go through the nickel oxide, where in the ruthenium they just fly through, and you'll have an exchange of angular momentum between these 2 systems. And if you then look at the nickel oxide space system, from up to down, down to up, the demagnetization states are more or less the same time states. Yeah, so they fall on top of each other. If you do that for ruthenium, where there's an exchange of angular momentum between the 2 layers, you see that there's a difference. So there's a little bit difference in time when you have the lowest demagnetization for the same fluence. And that is actually a proof that there are spin currents generated by the ultrafast pulses, manipulating them further away in the system. So the exchange of angular momentum can also be non-local, further away. So we can use this to manipulate layers a bit further on. So you can think of this putting an antiferromagnet somewhere compared to a synthetic ferrimagnet or a ferromagnet to generate. All right, this was used further, for instance, in these kind of experiments where they use an iron layer and a gold layer, where you can pump from the back, detect from the top, and by the inverse spin Hall effect of the heavy metal on top, you actually generate terahertz waves. Well, we have seen quite a bit on this concept before. This is the concept that I just showed before. So there's follow-up work there where you have 2 ferromagnetic layers spaced by either a conductor or a non-conductor, where you can exchange the magnetization or the angular momentum between them. And finally, you can also use that, of course, to demagnetize the PMA layer, out of plane magnetized, and an in-plane layer. So these are non-collinear, the 2 cases. So you have maximum torque transfer to the other layer, and you can generate dynamics in the top layer. So there's already quite some proof out there that this should work. And I hope you all agree that this is well established now. All right, so there are a couple of models. I want to go into the theory, more models. I'm more of an applied physicist, so I like to think more in models. So the first one is ballistic injection of hot spin electrons from the ferromagnet into the normal metal to somewhere else where you can use. Other nice models by OpenAir, for instance, is super diffusive transport and spin filtering, where you have to play around with the spin lifetimes of the 2 species of the spins flying around. Spin-dependent Seebeck effects, where thermal gradients that you generate to the heating also generate spin currents into the system. And DMDT kind of models, where it's really the SD model of transport, where you actually generate angular momentum by demagnetizing. It has to go somewhere. It can also go to the spins, and thereby you get it in. So angular momentum transfer from the demagnetization of a magnetization that you transport through. So these are the kind of flavors that you can use to describe these kind of processes. Now, coming back to this demonstration of all optical switching in the ferromagnets alloys in this case, so gadolinium iron or gadolinium iron cobalt. you can use this local and non-local transport a little bit better to understand what is happening in these systems. So where is this transport coming from, and how can you then switch magnetization? Now, this was already shown. So toggle switching at every next pulse, the magnetization switching back and forth due to the interplay between the cobalt, iron lattices and the gadolinium in there. One has a slower demagnetization time where you can play around with this toggle switching, as already well explained by Alexei in his introductory talk. So what is behind it? We've seen it before. When you have the iron and the gadolinium, you hit it with a laser pulse. The iron quickly demagnetizes. The gadolinium is much slower, so you have a transient ferromagnetic state. At that moment, you have a lot of exchange scattering, which you can see as local spin transport. Thereby, you push the system into the opposite state and they remagnetize in the opposite direction. It's extremely robust and it works every time. So you demagnetize the magnetization. Iron demagnetizes much faster than the gadolinium. You have this transient state where there's a lot of exchange scattering. You can see that there's a local transport of angular momentum between the two lattices, and thereby you actually get the switch of the system to the other state. Extremely robust, and we have been reproduced in many, many labs. All right. We have modeled this using this local transport, these models that we had before, by Maarten Deens, this guy up here, in the alloy system, so cobalt gadolinium alloys, and in the bilayer system. Actually, this is the composition of the system. So you have a randomized alloy system, or you have a layered system where you have 3 layers of gadolinium. And then depending on the amount of cobalt layers on top, we look if we can also switch that. Now, the alloy system is very, very sensitive on the composition of the alloy. Now you can see that within, 5% of alloy composition of the cobalt and the gadolinium, you only get switching in a small pocket. So this is energy versus composition that you have there. If you go to the bilayered system or the layered systems, the only thing that's relevant where this exchange scattering is happening is at this interface. And that composition is independent about how many cobalt layers you put on top, right? So you have a local system where magically all the switch happens from here, and that actually folds into the system upwards. So you can see that as a domain wall front going through on an ultra-fast timescale. It's a bit of a strange way of looking at it, but it's an interesting concept. And the nice thing is you can play around with a lot of cobalt layers. Now you can make the ferromagnet on top very thick, and the process will always happen, at least within these models. So we've played around with that, and that is actually true. So in all the experiments, we can put a lot of layers on top. It can go up to, I think, 8 nanometers of cobalt nickel repeats to keep a PMA, but it still switches. So a very nice, robust way of looking at it. All right, so how can we use that further? Spin a current-assisted all-optical switching in cobalt gadolinium. I will use that to use a deterministic way of switching a bit. Now it's toggle switching. So every time you come with a pulse, it either switches, or if you have too little fluence, it does not switch. But you can't do it deterministically, which is a bit annoying for logic. So we found a trick that we can actually use assisted all-optical switching by parallel and anti-parallel states. Come back to that. Now I'll have a Fourier view on the mechanism of femtosecond spin currents that we generate. Then we will try to resolve the spin currents from a cobalt gadolinium bilayer. Where is it really coming from, the spin current? The cobalt or the gadolinium? And we already had the treat from Davide that he showed that we can then do it in the gigahertz or in the terahertz regime. And then finally, I'll show a little bit results on how we can do current-induced domain wall motion in these synthetic ferrimagnets, as I started with. All right, so we engineered this stack where we have a big repeat of cobalt nickel layers, a copper spacer, and then cobalt gadolinium. Now, if we shoot a laser pulse on this, of course, all the layers generate angular momentum in the spins that are generated, right? They demagnetize, angular momentum has to go somewhere. So the angular momentum is deposited from the top, but also the top down. The gadolinium, for instance, also influences the cobalt, which is the local exchange that you have, the exchange scattering that I introduced before. Now, if you have the magnetization like this and like this, so for the cobalt and the cobalt aligned, we call it the parallel state. Now, the electrons transported from here to here, they are collinear, so though they will not excite any spin dynamics. They might excite it in the gadolinium, but they're fully absorbed already in the cobalt. So in this case, yeah, it's hindered. It doesn't help. The spin current doesn't help the switching that we generate. If you have the anti-parallel case, so this one up, that one down, the spin current that you generate over here will actually be anti-parallel to that one, and thereby generate a spin transfer torque on the system, and thereby help actually the switch, right? So if you look at the domain size that you generate with a single pulse as a function of laser pulse energy, and we look at the anti-parallel to the parallel case, so actually from the anti-parallel to the parallel case, we find this fluence density. So it starts to switch at 200 nanojoule in laser energy. If we do the other case, you need more energy to switch. So this is an implicit proof that these spin currents have an asymmetry depending on the local orientation of the two states, right? As we know very well from spin transfer torque systems. So we now can use this to make a deterministic switching between the two. Now, how does that work? Well, Yuri came up with this idea. It's nice for logic, maybe, but toggle switching can't help. So what can we do? So what can we do? We can generate different threshold fluences. So pulse 1 is below the threshold fluence for complete toggle switching, where both layers will always switch, where you always switch the other way around. So you set it with your first pulse. All right, so we start with this state. One is prepared in the anti-parallel state, one in the parallel state. And if you shoot a laser pulse on the anti-parallel state, it will switch. However, if you do that on the parallel state, it will not switch. So you don't see any change of the contrast. Now, if you do that with the set pulse, so we have done this, and then we do a toggle pulse, right? With the toggle pulse, it will always switch. So now you have generated the state in the end, which is deterministic. We always wanted to switch the state, which is in this case, so we can call that a 0. In that way, you can use ultrafast switching now to really deterministically set the bit state that you want into the system, just by using these ultrafast spin currents that are generated. All right, now we can take that one step further. We again have the out of plane layer. Now we have an in plane layer, which you can play around with the thickness, and you can dump the angular momentum of the out of plane layer into the top layer and generate dynamics in this top layer. You will generate two kinds of dynamics. One is a standing wave in the vertical direction, and depending on the thickness of that nanometer layer, that's in the terahertz range. Yeah, it ranges from 0.1 terahertz to 1 terahertz. And that's what you see after the demagnetization as a function of time. You see this wiggle, terahertz waves. So it's a standing wave in the thickness. And on the longer term range, you just have the ferromagnetic resonance of the whole system that is coming back if you do it in a field. Right? So you can play around with the terahertz range and the gigahertz range. All right. Now, how can we understand that one step further? Which mechanism is behind it of these 4 models that we used? Now, we tried all 4 of them. And actually, the last one, the DMDT model, fits best. And I want to show you how we do that. So we measure a DMDT in the experiment. So DMDT, we take this one. Then we take the generated spin current from that profile, which then looks like this. So I put a minus sign so you can see it goes positive. So if you demagnetize, you create a spin current. It remagnetizes. If you take the derivative, it's negative. And this is the kind of spin profile or injected spin current that you have in that system. Now, we're lazy, so we input it into a mu-max simulation where you just have a kind of equivalent torque that you get to the system, and we see what kind of dynamics that you induce in a system like that, also on the terahertz range. So this is the result for mu-max simulations, yeah, or LRG simulations that you have. In the beginning, you have a quick overshoot, and then later on, you can fit really the profile that you get out. You can profile the frequency, the amplitude, and the phase of that system, yeah, depending on all kinds of input parameters that you have. Now, if you look at the terahertz experiment that we do, so this is really, again, the terahertz result, you can see that we can really extract all these parameters. Yeah, so we can fit the amplitude, the phase, to find back what the profile is of the generated spin current. So the terahertz range is tuned by the thickness of the in-plane layer because it's a standing wave in this whole system. And the gigahertz range is tuned by the external field that we apply when we do the experiment. So these are the results of the terahertz range. So this is the fluence dependence of the pulse shape. So increasing fluence, you see that you have more demagnetization. So the amplitude increases. Moreover, you see that you have a phase shift. The minimum is shifted to larger time, indicated by the red line. Now, if you look at the experiment, this is the experimental resolution that you have. We find the same thing. You have a shift of the phase, and also the frequency scales in the same way of the system. Right, so there's a pretty good correspondence between the two to find how that works out. Now you can plot them, put that back in the mu-max model to really find these frequencies. And in the blue lines, you see the simulations, and in the green lines, the experiment that we find of the spin wave phase. Yeah, so if you inject the wrong phase, then you shift it by 180 degrees, etc. So this is really results that indicate, it's not a foolproof, but it indicates that the DMDT model is a very nice result that we have behind it. Moreover, we cannot match it with the other model that we have, where we have ballistic excited carriers to the other side. So that's a nice proof there. I'm already running out of time. My apologies for that. I'll hurry up. So non-local spin transport and all-optical switching, there has been reports where you have cobalt, gadolinium, iron, copper, and cobalt platinum, and want to switch the whole system by generating the systems like that. So if you create a current, you also switch the other one to the opposite sides, as presented in this work. So Tom asked the question, can we quantify the spin current generation by gadolinium? Yeah, so this is an alloy. You can't really say what is coming from the gadolinium or the cobalt. So you have to use a multi-layered system that at the interface, you only have gadolinium. The spin current is then from the gadolinium transported through the system and not from the cobalt. Well, in a bilayer or a multi-layer system, you can do that. So this is the experiment that Davide already showed. So we have a cobalt layer, gadolinium layer thickness that changes its thickness over many millimeters. So we can do local probing. And then we have a spacer and we dump it again into an in-plane magnetized cobalt layer. Now, if it's thin, it's dominated by the spin species of the cobalt. If it's thick, it's dominated by the spin species of the gadolinium. So we can play around with where they're coming from, fast demagnetization or quick demagnetization. So this is the slide that we showed before. We already showed that the spin current generated is proportional to the DMDT. And this is the cobalt demagnetization. It's quick. The gadolinium is slow, terahertz, gigahertz. Same thing there. So these are the results. So this is the thickness of the gadolinium that we put in between. So the magnetization is a function of time delay. And if you plug that in, you see that for cobalt, we have 0 phase shift. And then for a very thin layer of cobalt or gadolinium actually adding to the system, you actually directly go to the spin current generated by the gadolinium. Yeah, so you have a direct thing. If you model it with the SD model, so the DMDT and the SDT model together, you can directly reproduce the whole system that you have. Right, so sign changes from cobalt dominated to gadolinium dominated. That's around 0.7 nanometers that you have here. So that's also the length scale where these spin currents can't go through or originating from. If you go to the gigahertz range, the terahertz range in the thick gadolinium system, you see that you have nearly constant phase, but we do see that the amplitude of the generated waves go down. So thereby you see that this is very inefficient in generating these very high frequency modes. So there's a decaying contribution of the fast cobalt spin current injected into the second layer that you have here. All right. This is actually the main conclusion, the take home message. Non-local spin transfer, gadolinium slow, cobalt fast, or iron, the other ones. The MDT mechanism is something that really works out in our experiments. Maybe use that also for antiferromagnetic tricks to manipulate that ultra fast. Now, if you indulge me, I have 2 more slides to show. Thank you. So the last bit I want to show all optical switching and current-induced domain motion in this device concept that I introduced at the beginning. So coming back to that one, combination of photonics with spintronics. Now, what do we need to show? I already showed you that we can do high domain wall velocities. So these are in the synthetic ferromagnets. Now, what we have done with the trick, this first part has been shown by Parkin already. So cobalt gadolinium bilayer synthetic ferromagnet, it has a compensation temperature at 220 Kelvin. Can we pull that towards room temperature? Well, you can do that by just adding a cobalt and a gadolinium extra. Why? Because you now have 3 interfaces where the gadolinium is induced magnetized. So you have more magnetization of the gadolinium, so you can pull the compensation temperature to room temperature. The nice thing of that is, if you start with the domain wall velocity as a function of this middle gadolinium thickness, you can find that the domain wall peaks, at least for low current densities, exactly where you expect it at the compensation temperature, or thickness in this case, it's also temperature, thickness of the gadolinium layer. If you start to push high currents into the system, so going up to 3.5 teraamps per square meter, you see that this maximum velocity, which is high, 2.5 kilometers per second, shifts to higher gadolinium thickness. Why? Because during the current pulse that you apply, the Joule heating is heating up the system, and thereby also you go away from compensation. Compensation then only happens at thicker gadolinium thicknesses. All right. The nice thing of that one, Fluence dependency of these multi-layered systems, is that at the compensation point, the gadolinium thickness, you also have the lowest fluence to actually switch the system. Something that we do not understand fully yet. So theoreticians, please explain this to us. This is a puzzle that we're still trying to solve, actually. It has to do a little bit with the Curie temperatures, of course, that you create in these gradients in the gadolinium. It's then position dependent in the thickness, but yeah, the full puzzle we haven't solved yet. All right. Wrapping up our device concept that we are trying to generate, and I hope that we can do this in the future with antiferromagnets to really go to the ultimate high speeds that we would like for the solutions. All right, and with that, I would like to finish and thank the group for their contribution. Thank you.